Okay. Okay, so not too many of us yet, but so my internet today is working so. So if I freeze, or maybe more importantly, if my iPad freezes, please let me know. So in my previous class there was this issue where when hang on, I think I know what's going wrong. Yep, so there was an issue when people would stop seeing anything that happens on my iPad, which is the main thing that happens in class anyway. So if you see that the screen is frozen, please let me know as soon as you can. All right. Going to zoom out a little bit. Okay, so this was an indented path. Let me open this and this. Yep. Okay, so I want to do another exercise before we move on. So just to remind you everything about our technique and our strategy. Okay, but before that I need to see the chat. Here's the chat. Okay. Yeah. So one more example. Let's do cosine of x. So we know that if we integrate cosine of x divided by x from minus to plus infinity, we should get 0. So we will do x squared from minus infinity to infinity. And still we'll replace cosine of x with e to the ix dx. Yeah, and by the way, back to the question, how do we know what's x and what's z? So the original problem is given in terms of x always. Well, not always, but here. So this first conversion, we don't replace x with z. We are going to replace x with z now. So we'll look at this function. And what's our contour? So our contour is the same as it was on Wednesday. So we need to go around the origin, and then we have this circle. We need to go around the origin because at the origin we have a problem. So it's fine if the problem is inside the contour. It's fine if the problem is outside of the contour. But it's not fine, it's actually really bad when the problem is on the boundary of the contour. So, and when the problem is such on the real line, we always kind of go around like this, as shown. So this will be my CR, and because inside of CR we don't have any singular points anymore, we know that the integral here is 0. And now let's split the integral over CR. I need to write f of z. I'm just trying to save some space. So instead of f of z, I'm writing f dz, but the argument is z. Okay, so we have this picture. Okay, so we integrate over this part, then we integrate over this part, then we integrate over this part, and then finally we go this way. And so I wrote arrows everywhere. Okay, now we will realize right away that this goes to 0 as r goes to infinity. That's the Jordan's lemma. Let's recall, what does the Jordan lemma tell us? It tells us that if we have the exponential times something small, then the integral will go to 0. Okay, and we do have the exponential times something small. So when we are on this part of the contour, we have absolute value of z is equal to r, so 1 over z square is like 1 over r square. It's pretty small. So Jordan's lemma tells us that, sorry, not sleeping enough. So Jordan's lemma tells us that the integral over this semicircle will go to 0. Okay, now our lemma from the previous time tells us that the integral over this semicircle goes to minus pi I times the residue of f at 0. As what? As epsilon goes to 0. Because remember, this little semicircle has radius epsilon. Okay, Ryan wrote same. What does same mean? If nobody hears me, write something, especially if you heard this. Not sleeping enough. Okay, great. Well, no, not great. But because it's almost like a vacation, my sleeping schedule got messed up. Yeah, sorry. I just got worried that someone wrote in chat that cannot hear anything, and you wrote same. Okay, great. So if you can hear me, that's perfect. All right, so this goes to minus pi I times the residue at 0. And what is this? So let's look at this part of the path. So this is minus r here, this is minus epsilon here. And this part of the path is on the real axis. So on this part of the path, z is real. And so this part of the path is the integral from minus r to minus epsilon into the ix divided by x squared dx. And this similarly is the integral from epsilon to r to the ix over x squared dx. Now let's imagine that epsilon goes to 0. If epsilon goes to 0, it means that we take this minus epsilon and replace it with 0. And we take this epsilon and replace it with 0. And then what do we have? We have an integral from minus r to 0 plus the integral from 0 to r. So these integrals add together and we get an integral from minus r to r. And then when we set r to infinity, that's embarrassing, we get an integral from minus infinity to infinity. And this, in the left-hand side, this is always 0. This is 0 no matter what r is. So we have 0, is equal to the integral from minus infinity to infinity e to the ix over x squared dx minus pi I times residue of f at 0. And so this integral is just equal to pi I times the residue. So our only goal is to find the residue. And honestly, let's see, I don't need power series, right? Because I can just say that this is phi of z, and so the residue of f at 0 is just phi prime of 0, which is I. Okay, hang on. Now, am I happy with this? Yep, I'm okay. I'm okay with this. So what do I know? I know that 0 is equal to the integral from minus infinity to infinity e to the ix over x squared dx. Now I'll be careful. Minus pi I times I. So I times I is minus 1, and minus 1 times another minus 1 is plus 1. So I got plus pi. And so this implies that this integral dx, forgot dx here, is equal to minus pi. And so integral over of the cosine, which we're looking for, is the real part of this, because cosine is the real part of e to the ix. Is minus pi. And that's the answer. So we got a negative answer, which is absolutely okay. We got negative answer, which is absolutely fine, because nobody actually told us that the answer should be positive. Cosine oscillates. And so it's perfectly allowed to give us a negative result. I mean, to give us a number that is negative. Okay, so this was a reminder of what we're doing last time. Now we'll do two more important things that involve these indented paths. So, okay, the book calls it an indentation around a branch point. So it won't have any extra theory. We'll just try to come up with some recipes about how we deal with problems. And so we will just have examples. So let's do this. Okay, and so there are many problems here. One of the problems is that we cannot possibly write this as an integral from minus infinity to infinity, because logarithm is only defined when we're positive. So if you look at the book actually likes to integrate from 0 to infinity, and then using some using some even functions or odd functions, move on to an integral from minus infinity to infinity. We did this a couple of times. You know, when we integrate from minus infinity to plus, from 0 to plus infinity, and then we say that our function is even, and so this is just 1/2 times the integral from minus to plus infinity. Well, this is what the book really likes. And I was trying to avoid this step just because the step doesn't have anything to do with complex analysis. But here, unfortunately, we must integrate from 0 to infinity. However, as soon as we introduce this function, logarithm of z divided by z square. Sorry, I'll redo. Logarithm of z divided by z square plus 4 square. This function is defined everywhere, except that we need to define the branch. And here I strongly suggest to first draw the picture and then see like which branch cut to have. And finally, it will be somewhat justified why did we talk so much about these different branch cuts. Okay, so our ultimate dream is to use the same CR we used before. Okay, so this CR. So imagine that our Z lives only on this contour. Then what does it make sense to cut out? Well, our usual choice was to cut this out. Yeah. But this is not a good choice here because remember I told you that we really don't want to have any problems on the contour. We don't want to have any problems on the contour. And cutting out this ray actually gives us a whole bunch of problems on the boundary of the contour. Well, cutting out this, for example, is also bad because it's okay to have 1 or like 10 problems inside the contour, but here we have too many. If we cut out this, we'll just have too many problems on the contour, and moreover, these problems won't be poles, which is bad. But then there's a really perfect choice. And the perfect choice is to cut out this. So if we cut out this and therefore allow our theta to run runs from minus pi over 2 to 3 pi over 2, then that's perfect, but it's almost perfect. There is only one problematic point on the contour, and it's this one. Okay, so this is the point that we also want to cut out. The origin is very bad from the logarithm point of view. And no matter which branch cut we consider, we'll still always need to cut out the origin. So really, well, origin is a problem, but we cannot avoid it. And so the way to avoid it is to modify the path a little bit. So we will follow our path, and then as soon as we come close to this point, we will go around it, like this. So we'll actually have the same contour of integration that we had in the previous 2 problems. And now everything is perfect. Now life is awesome. Because now we cut out this green ray. It has nothing to do with our new contour. So in our contour, on our contour, and inside of our contour, our logarithm is a nice and analytic function. And so this means that by the residue theorem, if we integrate f of z dz over our contour, it will be 2 pi I times the residue times the sum of the residues. Now let's look at f. So inside this contour, f has only one residue, and it's at 2i. Okay, so where are the singularities? Well, the singularities is when the denominator is 0. And the denominator is 0 at plus or minus 2i. So 2i is here, minus 2i is here. Minus 2i is not in our contour, so we don't care. And 2i is in. So this is what happens. And let me compute this residue right away, just get it off our heads, because then after we compute the residue, we will go into like bigger problems. We'll try to compute how does the integral of f behave over here. All right, so how do we write f? Well, we'll factor the denominator. And we're doing the residue at 2i. So we'll call this thing phi. So this thing will be phi of z. And we know that the residue of f at 2i will be phi prime of 2i. Okay, so that's pretty terrible. We'll need to differentiate phi. Well, let's do it. So it's 1 over z times z plus 2i squared minus 2 times z plus 2i logarithm of z divided by z plus 2i to the fourth. All right, and now we need phi prime of 2i. So in particular, we are going to need a logarithm of 2i. And what's logarithm? It's logarithm of r plus I theta. So what is r? R is 2. And now we need to compute the theta. So let's look back at the picture, or here our theta ranges from minus pi over 2 to 3 pi over 2. And 2i is over here, so its argument is pi over 2. So theoretically, I could have got like 5 pi over 2. But fortunately, I kind of wisely chosen the range of theta. If we chose a different range of theta here, like you see, we could do from 3 pi over 2 to 7 pi over 2. Then we would eventually get the same answer. And yeah, and you'll hopefully see why. Because we'll take real parts. But anyway, that's logarithm of 2i, and what's phi prime of 2i? So it's 1 divided by 2i times 4i squared minus 2 times 4i times logarithm of 2 plus I pi over 2 divided by 4i to the fourth. Okay, pretty terrible, as I said. We can simplify this slightly. So 4i squared divided by 2i will be 8i. Here it will be 8i minus 8i logarithm of 2. Okay, plus 4 pi. Why plus 4 pi? Because I have a minus here, and I have an I and an I, which will give me another minus. And then these two cancels out with these two, so I have 4 pi. Divided by 4i to the fourth, which is the same as 4 to the fourth, which is 2 to the 8th, which is 256. Okay, so and now 4 cancels out, so we'll just get 64 here, and here we have pi plus I minus, no, pi plus 2i minus 2i logarithm of 2. So this is my terrible residue. I don't even want to check it. Yeah, I actually found it in the book, and it's correct. So I encourage you all to do this slowly. I did it very fastly because I tried to do all the I did all the algebra very quickly, but I really encourage you to do this and see that my answer is correct. Okay, so conclusion is that the residue of f at 2i is pi plus 2i minus 2i logarithm of 2 divided by 64. Great. And now, on the other hand, we know that the integral of f over this CR. Let's go back and look at the picture. So we again have 4 parts. We have this part, this part, this part, and this part. Okay, so it's integral from minus r to minus epsilon plus the integral from epsilon to r. These are the horizontal parts. Okay, plus the integral over this small fellow, plus the integral over the big fellow. Now for the integral of the big fellow, this goes to 0. So we cannot use Jordan's lemma anymore because Jordan's lemma needs an exponential, but we can use our good old brute force method. We can just take the function and estimate it. Because I will do it quickly. Z squared plus 4 squared, it's less or equal than this. And we're proficient in the denominators. We can get this, for example. And the denominator will ultimately win because we know that a power is always, more powerful than the logarithm. This is what you know from calculus. So no matter how I estimate this, I actually want to leave it as an exercise as well, just for you to exercise, or you can see it in the book. But anyway, no matter how do we estimate this, it will be something like logarithm of r, or actually natural log of r. And the power will beat natural log of r. And then we need to use our usual estimate. So we need to multiply this. We need to multiply this by 2 pi r or by pi r by the length of the contour. But anyway, we have enough powers of r in the denominator to kill the logarithm. All right, sorry. So this fourth term will disappear. Now I want to look at this term. I want to look at the integration over small circle. And in fact, this will also disappear. Because you see, we don't have, well, we kind of do have a pole here. But it's actually not, it's not really a pole. A pole requires something like a negative power. And here all we have is a logarithm. So I'm going to prove that this goes to 0 as well, as epsilon goes to 0. Why is that? So we need to be careful here because I'm going to use our usual estimating procedure. But we used it like 50 times so far, and every time we try to prove that the function is small enough to beat the large path. Here, the path helps us. Here, the path is very short. Length of the path is pi times epsilon. So all I need to prove is that the function is not big enough. Okay, so how do we do this? We still need less or equal. That's good. But for example, to estimate this, I still need to estimate this from below. And I always did this because z was huge. But now I will not. Now I will do this. And this is 4 minus epsilon square. Okay, so remember that we always have two choices. We can either do a minus b, or we can do b minus a. And we always choose whatever choice gives us a positive number. So if epsilon is small, then this is a positive number. So here I choose to rearrange the terms. And now I need to estimate the logarithm. So what is logarithm of z? Logarithm of z is the natural log of r plus I times theta. Now what is r? R is the absolute value of z, and the absolute value of z is epsilon. Oops. So I'll get the natural log of epsilon plus I theta. Now I need the absolute value. Well, I'll just compute the absolute value honestly. It's logarithm of epsilon square plus theta square. But my theta has a range. Theta cannot go all the way to infinity. Theta goes only all the way to 3 pi over 2. And so this is less or equal than this plus 9 pi square over 4. Now, you're probably looking at all this now, and you're asking yourself, how the hell do I come up with this? It's actually not easy. So if you expect such a question on the test, you can also expect a hint. But there are some recipes. So recipe number 1 is that we never have a denominator estimated from below instead of from above. Second recipe, if you have something like this, then make a choice. So either this or this. And the third recipe that we haven't seen yet is that if you have the logarithm, write its absolute value by definition, and you can always expect a theta term to do nothing. Okay, so for the theta term, just write the largest possible theta there is. Okay, so on this path, we have what? We have f is less or equal than this. Divided by this. And so the integral over this path and I keep forgetting to do this, but I also need to write it where on the top part. Is less or equal than the length of the path times the maximal value of f of z. And this goes to 0. So this is like a real valued limit. And what do we have here? Well, this actually just goes to 16. So this doesn't hurt. What hurts is the logarithm, because logarithm of 0 is minus infinity. But we know from calculus that epsilon always beats logarithm of epsilon. And so this will go to 0 as epsilon goes to infinity. Oh, sorry again. So you can try to use a fancy L'Hopital's rule, and you'll see this. But the reason is that the limit of x times logarithm of x is 0 when x goes to 0. So this is a fact from Calc 1, I think, or Calc 2. Calc 1, I guess. And so this integral also goes to 0. So what we're left are these. Yep. So we need to figure out what is this. And notice that I cannot do my usual thing because my f of z is very nicely defined here because f of z involves the log. But f of z is not so nicely defined here because I'm going to get logarithm of a negative number. So I'll need to figure something out about this integral. So see, it actually becomes a long problem. Okay, so when z is on minus epsilon minus r. And now if we're not sure, and even I'm not sure because I'm not looking in the book on purpose, so if I'm not sure, I'm just going to honestly write the parameterization. So my parameterization is gamma of t is equal to t, and t is from minus epsilon to minus r. So gamma prime of t is 1. That's great. What's f of gamma of t? So it's, yes, it's the complex logarithm of t divided by t squared plus 4 squared. And what's logarithm of t? It's the same as nature log of absolute value of t plus I times theta. Okay, I'm trying to really slow down here because here will be the conceptually important part. Okay, and what is theta? So let's recall the picture. So we're talking about this part. We're talking about this line segment. On this whole line segment, theta is equal to pi, because here are my y-axis, here's my x-axis, here are my x's. And so this line segment, it's on the left from the origin, and so here theta is always equal to to pi. So this is actually logarithm of absolute value of t plus I times pi divided by t squared plus 4 squared. And now I need to integrate it. So integral of f of z over this line segment is equal to this. So integral from minus r to minus epsilon logarithm of absolute value of t plus I pi divided by t squared plus 4 squared. And now I can make a change of variables. I can make a u substitution, or I will make an x substitution. I will plug x equal to minus t. I'll plug x equal to minus t. Then dx is minus dt. And this limit will become plus r, and this limit will become plus epsilon. And oops, and x is now positive. So I don't need absolute value here anymore. T was negative, x is positive. Plus I pi. Well, t squared and x squared are same things. And sorry, yeah, dt, but dt is minus dx. So times minus dx. And how am I going to destroy this minus? Well, I'm going to destroy this minus because my limits are very weird. I don't want to integrate from r to epsilon. It's backwards. I want to integrate from epsilon to r. So I'll change the order of limits, and therefore this minus will disappear. So where did we start? We started here. And it turns out that this first integral at which the arrow points is almost the same as the second integral, except that it has this extra term, which is ugly, but not very ugly. It has this extra term. I'll actually write it like this. And this, I'm pretty sure we've done. Or at least we know that we can compute this integral. Well, after we replace epsilon with 0 and r with infinity, we can compute this integral using residues. But hopefully we won't need to. So let's see. So now what do I have? Okay, I'll scroll back a little bit. Well, okay. Sorry, my finger doesn't work for some reason. Here we go. So I have this integral is equal to this integral plus this extra term. So altogether they'll be 2. So I'll get 2 of these integrals plus the extra term. So now after sending epsilon to 0 and r to infinity, our integrals over this curvy part of the contours will disappear, and we will have this. And this is equal to the residue. Where is my residue? Here, here is my residue. Here is my residue to pi over 64 pi. What was there? Minus. I'm still not looking at the book. Plus 2i minus 2i logarithm 2. Now, what is super cool? Okay, hang on a second. Hang on. So I messed up. Yes, yeah. Sorry. This is where I messed up. This is my phi prime of 2i. This is my phi prime of 2i. So I messed up in this line. This is my phi prime of 2i, but no, sorry, I didn't mess up. I didn't mess up anything, but I need to take the residue and multiply it by 2 pi I, because the residue theorem tells me that I need to multiply my residue by 2 pi I. There we go. Okay, awesome. So what's going to be equal to? It's pi square over 32i minus 4 okay, so plus okay, 2 cancels out here, 2 cancels out here, so 16 pi logarithm of 2 minus pi, something like that. Okay, check the algebra. I'll check the answer from the book at the end. But my point is, so here's another important point. So algebra is not important. Algebra is something you can always check by hand or double check. I mean, what's important here is that this is the real part. This is the imaginary part. This is the imaginary part, and this is the real part. So I care only about real parts. My task was to find only this integral. So I will just take the real parts and I don't need to compute this integral at all. I could, but I don't need to. So now you divide by 2 and you get the answer. So logarithm of x divided by x squared plus 4 squared dx is pi logarithm of 2 minus pi divided by 32. So this was a half an hour example. So I guess it would be too much for the final, although, so I mean, if we didn't have this all virtual, I would be more comfortable signing bigger homeworks to you and doing more examples at the board, and would probably get proficient enough to go quickly through some of the steps. Then this example becomes faster. But it's still long. So like you really cannot do it. There's really no shorter solution, is what I want to say. You can go faster through some of the steps, but you cannot replace any of the steps with something easier. And see, the only reason for this was that logarithm is very badly defined at this little point here, the origin. Okay, so I guess I'll stop here. So next time we will do integration over branch cuts. So an advertisement for the next time. Next time we'll consider a contour like this. So if you're playing, for some reason it reminds me of the Pokemon Go ball, but we'll have this non-integer powers of x that we'll need to integrate, and so we'll need to kind of artificially erase the whole array. So this will be our contour for the next time, and we will then do some very funny application to Laplace transforms. At first I wanted to skip it, but then I thought that it's a nice connection to your ODE class. So after we do a horrible, like another 30 minutes example with this picture, we will do some applications to Laplace transforms, and then for the rest of the time we'll do what's called conformal mappings. All right, so thanks for sitting through. I know it wasn't easy, and I'll see you on Monday. Try to get some sleep over the weekend.
You too, buddy. Get some sleep.
Thank you. Yeah, good job pressing the space. So, bye-bye.